Okay, moving on to electric fields and electric force, electric energy, and eventually something we call electric potential. Right off the bat, I'm going to remind you that electricity is a little bit more complicated than gravity. Electricity is created by charge, but unlike gravity, gravity was created by mass. We only have one kind of mass. We have two kinds of charge. They had opposite property. This charge existed kind of in two states. So in a clever decision, they chose to call one of the kinds of charge positive and the other kind of charge negative. That's going to help us later when we get into math. But already that means it's a little bit more weirder than gravity. Gravity just had mass. Electricity is due to charge, and there's two kinds of charge, positive and negative. Any object with charge is surrounded by an invisible electric field. Just like gravity, just like the map of the wind, it's a vector field. It's a bunch of arrows that indicate the direction. In this case, it's the direction of a force. Like gravity field was a direction a mass was pulled, the gravitational force. In this case, the electric field is the direction of the electric force. But because there's two kinds of charge, we have to be more specific. The electric field is the direction of the force on a small positive charge. And here I typed mass, but it would have made more sense if instead of mass I said charge. So I should go back and edit that. For example, let's say classic science experiment, or maybe goofing around as a kid. Let's say you rub a balloon on your hair, and as a result, the balloon becomes positively charged. So static electricity stuff from grade 9, electrostatic series. There's a transfer of electrons. These wee tiny little electrons leave the balloon and go into your head. So your hair might stand up, but we're focusing on the balloon. We're saying the balloon becomes positively charged because it gave some of its electrons away to your head. Now, what electric field is it's a bunch of arrows that indicate the force that our balloon would put on a small positive. If it's the balloon is positive, and we always imagine a positive, that's just how we do it. When they invented field theory, they always thought about small positives. If we put a small positive near a positive balloon, positives repel each other, so the small positive will get forced away. So we say that the electric field around a positive charge always points away from the positive charge. That's just what it is. If we switch it, maybe we don't rub the balloon on our hair, maybe we rub the balloon on our sweater. In static electricity, electrostatic series, let's say that when we rub it on our sweater, electrons leave our sweater and go into the balloon. That means the balloon has become negatively charged. If it's a negatively charged object, if we imagine what that negative object would do to a positive would get attracted towards it. So the electric field for a negative charge is this grouping of arrows that always point towards a negative. Because way back when, they didn't know really what they were talking about, so they always pictured small positives. So we can say, and this is as far as we got in grade 11, no, we got a little bit farther, electric field always points away from positive charges and towards negative charges. We're not going to do a proof for the electric charges, we're just going to build them by symmetry. Gravity is due to mass, electricity is due to charge. Mass we have called capital M and little m, and it's in kilograms. Electricity, the units are coulombs. Coulomb was a French guy that kind of did a lot of work on electricity. If you pronounce Coulomb with a French accent, his name is actually Coulomb. So since his name kind of pronounced properly, it has a Q sound at the beginning, the short form for charge is big Q and little q. Gravity is always towards, since gravity is boring and always attraction. Electric fields, there's two versions. Electric fields point away from a positive and towards a negative. Gravity is all about mass and always has this constant involved. Electricity is all about charge and always has this constant involved. For grade 12, we're going to keep it this simple, that the constant is this number. But when you swing back to this in university, maybe your professors will talk about how electric field will change depending on the medium. So this 9 times 10 to the 9 number that we're going to use, really that's the value in air. If we switch the medium, air and vacuum are both 9 times 10 to the 9, but if we switch the medium and it's not in air anymore, then that 9 times 10 to the 9 number would have to change. But for this year, we're just going to assume everything's in air. The field theory said things with mass are surrounded by an invisible gravitational field, and we can get the value of it by doing this math. The constant times the property divided by r squared. So we've got a parallel equation for electric field. Instead of lowercase, we call it capital case E for electricity. It's got a vector hat to show that it's a vector field. It's the constant, which in this case was k. The property is q, and divided by r squared. So really this is sort of the parallel to our gravitational field equation. The constant, the property divided by r squared. Now, unfortunately, notation is going to get a little bit ugly. We're going to use capital E for electric field, but I'll always do my best to, when I'm typing it, bold it. When I'm writing it, put the arrow on top, because electric field is the vector. Later, we're going to learn about electric energy. It's also going to be capital E, but energy is not a vector. So I'll put a capital E, subscript little e, subscript capital E to show that it's electric energy, but I won't put a vector hat on that one. One last thing, electric field is a weird one, but it's a force per charge. So its units are newtons per coulomb. Coulombs because that's the unit of charge. It's kind of like the 9.8 number. 9.8 was newtons per kilogram. This is newtons per coulomb. If objects are close enough together that their gravity fields overlap, then we get a force, and we know the strength of the force follows this one, Newton's equation, Gmm over r squared. Similarly, the electric force equation is going to look very, very similar. It's going to be the constant multiplied by the two properties divided by r squared. So k is the constant, qq instead of mm, divided by r squared. We know our law of electrostatics way back when, opposites attract and similars repel. It didn't matter for gravity. Gravity was always attraction, and we just had mass. We didn't have positive mass and negative mass. For electricity, there's going to be positive charges and negative charges. You kind of just use your brain, figure out whether the two charges I give you attract or repel. If they're the same charges, if they're both positive, we know they repel. If one's positive and one's negative, we know they attract. Because we know the direction using our brain, we don't have to put the negative, if we have a negative q, we don't have to put that negative q into our equation. Just put in the value of the numbers, and that equation will give you the value of the force, and then we'll use our brain to get the direction of the force. One more little bit, we can connect, there's a connection between the force and the field strength. Force is that field strength multiplied by the property. So this equation we used a lot in grade 11, and earlier this quadmester, gravity force is m times field. We're going to have a similar equation for electric force. Instead of m, it's going to be q. Instead of g for gravity field, it's going to be e for electric field. So electric force is q multiplied by e. That's our recap on force. We did that much in grade 11. What we didn't cover in grade 11 is we didn't talk about electric energy. Now that we've got our gravitational energy that we came up with this year using that cool calculus proof, our gravitational field energy was negative Gmm over r. We talked about it at length, but because gravity is always attractive, this gravitational field energy has to be negative numbers, and as you get further and further apart, it approaches zero. We've got a similar equation. We didn't tackle this one last year, so this is finally a new equation. If we have two charges close enough together to trigger a force, there's also energy stored in those electric fields. We can find the total electric energy. It's a parallel equation to the gravitational energy. The constant, the property divided by r. So electric energy is the constant, which is k for electricity. The properties are q and q, and then divide by r. One obvious difference is we don't put a negative into this equation. The negative in gravity was there as an artifact of the calculus and as an artifact of the fact that the two masses are trapped in proximity to each other, and positive work gets them farther apart. Energy is a scalar quantity, so when we're dealing with electric energy, if you've got positives and negatives, you do put the signs in. Like if you have a positive q and a negative q, put in a positive for the one q, put in a negative for the other q. When you calculate it out, a positive times a negative is going to give a negative electric energy. That's good because whenever systems are attracted to each other, or whenever objects are attracted to each other, their energy should be negative. So a positive and a negative charge should give a negative energy. If we have two positives or two negatives, they're repelling each other. That should be a positive energy. And putting your signs in will give you that. So as a quick recap, when dealing with force, electric force, we're going to use our brain to get the direction and not put signs into this equation. When we're dealing with energy, energy is a scalar. There is no direction to worry about. So we are going to put the signs into this one because negative energy is a little bit different than positive energy. So wrapping it up, a little summary here. Electric field is kq over r squared. Electric force is kqqq over r squared. Electric field energy is kqqq over r. The vector ones, don't put the signs into. The scalar energy, you do put the signs into because positive and negative energies are a little bit different. Okay, one last little thing. We came up with these equations for electricity, electric field, force, and energy by comparing to gravity. And we got Newton came up with those gravity equations by picturing apples and planets and moons, basically things that were round. As you get deeper into field theory, like not this year, but next year, maybe you'll learn about the electric field of like the antenna of your cell phone. The antenna of your cell phone is a funny shape, so you can't use these equations on the antenna of your cell phone because the antenna of your cell phone isn't round, which is kind of where these equations came from. Soon in grade 12, we're going to learn about parallel plates. When we talk about parallel plates, since they're not round, we can't use this group of equations. So this group of equations are great. We're going to use them, but they really only work for round charges. We got one more little thing, new thing to add to grade 12. The second new thing, we added energy. We're going to add another thing, but take some time and try these 3-4 examples. And the check-in questions are related to this topic and a worksheet there for you to practice as well.